Hello, my name is Stephane Hatgis-Kesse, and I am a computer science student at the University of Texas, Austin. This summer, I spent time working in Dr. Katja Sakar's lab here at Carnegie Mellon University, researching emergent communication for multi-agent reinforcement learning. I'd like to tell you a little bit about my project. Firstly, communication is essential for cooperation. Whether it be teams comprised entirely of humans, teams comprised entirely of agents, or some mix between the two, it's important that every member of this team communicates what they plan to do in order for the team to reach its objective. We can imagine this becomes even more important in partially observable environments, where agents do not have a complete picture of the state space. Take, for example, the simple traffic junction. Say we have two agents, but these agents don't know where each other are. This becomes a really difficult problem to navigate the traffic junction without collision. If, however, these agents are able to communicate with each other, they can inform their teammate of their current position and easily avoid some sort of collision. So this summer, I wanted to spend time investigating 3 questions. How can agents learn to communicate with each other and communicate well? How can they then use these communications to behave well? And how can they learn when to communicate? To address this first problem, we spent a lot of time on developing a general communication architecture. To illustrate, the first thing that happens is each agent takes their partial observation and encodes this using a simple LSTM. This gives us a continuous representation of each agent's observation. Now the problem is, how do we actually communicate this information in a useful way? What I worked on is implementing a vector quantized variational autoencoder. What this does is it takes our continuous representation and discretizes it. So our output is this discrete communication C. Having discrete communications is important because we as humans use discrete communications to communicate to each other. Fundamentally, this means that discrete communications should be able to communicate all that is needed to accomplish a given task, and they are more human interpretable. We train this general architecture to create these communications by maximizing the team's reward and by minimizing the difference between the reconstructed observation from this communication vector and the original observation. What this does is it generates communications that are beneficial to the agents and allow them to get better at completing the task, but it also grounds these communications in each agent's original observation, which both improves learning and allows for future work with human-agent teaming. So we have these generated communication vectors, C, which are then sent out to all the other agents and are used by each agent in conjunction with the agent's own observation to take an action at that time step. The question that remains is, when should an agent communicate? One could imagine why this is particularly important. For example, if we have teams comprised of both humans and agents cannot communicate all the time, otherwise they might overload the human. After all, we are fundamentally limited by our cognitive load constraints. Even with teams comprised entirely of agents, it still might not be a good idea to communicate all the time. Agents might be concerned about security threats or might be just fundamentally limited by their hardware constraints. To address this problem, we focused on designing a gating function, which takes in an agent's proposed communication and then decides whether to actually communicate it or not. The gating function decides whether to communicate this proposed communication by not only looking at the proposed communication, but also looking at all the previously received communications for this given agent. We then train the gating function to both maximize the task reward and adhere to a predefined budget that the agent must stick to. We find that when it comes to navigating traffic junctions that are partially observable, this general setup works pretty well. We are able to increase the range of budgets for which there is no loss in performance when adhering to that budget. This is compared to prior art that is able to restrain communication but requires a manual analysis of the communication sent, while our method is able to learn to remove communications. Additionally, we find through some further analysis that our learned gating function is able to remove most, if not all, uninformative communications, ensuring that agents are only communicating when they need to. For example, we can imagine these two agents here might want to communicate their observations when they first spawn on this traffic junction, and then again once they reach this intersection, but there's no need to really communicate in between those times. This is what our gating function is successfully able to do. A lot of work remains to be done. Firstly, our method suffers from high variance and training instability. Additionally, we should be able to take each agent's proposed communication and take the mutual information between this and what the agent already knows to see if it's beneficial to communicate this proposed communication from more of an information theoretic standpoint. This hopefully will alleviate some of the high variance and training instability problems that we've been facing. Another question, which is tangential to learning when to communicate, is learning who to communicate with. By exploring this problem, we believe we can further increase the range of budgets for which there is no loss of communication when adhering to those budgets. In general though, this has been a fantastic experience working here this summer, and I'm really excited about learning about emergent communication and all the progress that we have made thus far. Thank you.